Hi, this video is on vectors, and I'm following James Stewart's calculus textbook here. This is his chapter 13, section 2. It's not really that hard, though. It's kind of like we just now are getting around to some of these things. Well, let's start. So what is a vector? Well, if you've seen, what is it, Despicable Me, one of the bad guy in the first animated film is Vector, and he says, I have magnitude with direction. That's what a vector is. A vector is a quantity that not only has magnitude, but magnitude and direction. I think probably one of the nicest ways to explain this is to think of the difference in physics between speed and velocity. So speed doesn't, we could talk about me going 5 miles per hour, and we're not, direction doesn't matter if you're talking about it as a speed. So let's say that I'm walking 5 miles per hour in a big circle. I'm not going anywhere. But my speed, you could say, is 5 miles per hour, I suppose. Let's play I'm doing the shuttle run. I run from here to there and back, and here to there and back, and here to there and back. My speed might be, say, an average of 10 miles per hour back and forth. Okay, that's speed. It's just a magnitude. We call that a scalar, by the way. But what if I'm talking about velocity? Velocity, as physics talks about it, is not just a magnitude, it's a direction. And so if I do the shuttle run, and I run from here to here and then back, my average velocity is 0. Why? Because I've not gone anywhere. There's no displacement. And so velocity includes a direction. So sometimes you'll talk about I went 30 miles per hour, at an angle of 45 degrees from, the north or whatever. Or I went 30 degrees north. I went 30 miles north. That's a direction. That's a displacement. Or I went 30 miles per hour north. That's a velocity. Okay. A vector is usually represented visually with an arrow. So you, for the variable like an A or a B vector, you might see a little arrow on top of the A or a little arrow on top of the B. That tells you you're looking at a vector. Also, it can be put in bold. So a bold-faced A might indicate that it's a vector, whereas if it's not in bold case, then it might be a scalar. So a displacement vector has an initial point and a terminal point. Remember, it has direction. So it has a starting point and has an ending point. Two vectors are equal if they have the same magnitude and direction. Okay, well let's dig into vector addition. So what is vector addition like? So let's say we have two vectors. We have vector A, which is going like that, and vector B that's going like that. How do we add them? Well, the way to add them is you put the tail of one at the end of the other. And as we'll find out at the end of near the end of this video, you can do it in either order. That is, the commutative property of works. A plus B equals B plus A, and that works in vectors as well. So whether I put B at the tail of A or I were to put A at the tail of B, I'm going to end up with the same resultant. I'm going to come up with the same kind of resultant value or resultant vector for the two vectors I'm adding together. Okay, vector addition, pretty easy it looks like to me. You can also do vector subtraction. So let's take these same two, but let's subtract them. So what am I going to do? Well, I'm going to make B into a negative B. I'm going to flip its direction. And so instead of in vector addition, I put the B in its normal direction. But when I subtract it, that's like adding a negative, right? And so I flip it and put it at the terminal point, and then the resultant is like that, and that's vector subtraction. Not very complicated. This stuff's easy. Man, why did everybody tell me calculus was hard? Okay. Now, this here is called the triangle law. You notice that in both of these, I made a triangle. And so you can call that the triangle law, for vector addition or vector subtraction. But you can also do it with a parallelogram. We call it the parallelogram law. So let's say that I had an A plus B, and I wanted to add those two together. Well, I might just make a parallelogram out of it, and then the diagonal across it is the resultant. So that's another way to figure out a vector addition or subtraction using a parallelogram. the parallelogram law. One final thing, and that is scalar multiplication. By scalar multiplication, I mean I'm not multiplying vectors. That's something yet to come in the next two sections. Multiplying vectors is a little more complicated. But multiplying by a scalar, like let's say that I add a plus 2b, or not 2b. But let's go ahead and say to b. So 2b is going to be the same direction, but twice the magnitude. We're scaling it up. In fact, that's where the word scalar comes from. We're scaling it. And so scalar multiplication, if I multiply vector b by 2 and then add it using the triangle law there, that's the way that works. So it's really pretty simple. Okay, vector components. Now, this section of Stewart introduces this new bracket notation. This is vector notation. So see that those brackets there? Those aren't our normal brackets. So like take 4, 5 here. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay. So this is the point 4, 5 on this coordinate frame. But if I put them in this kind of brackets, then I'm no longer talking. Then I'm no longer talking about a fixed point. Now I'm talking about a algebraic vector. And so the position vector, we call this one right here the position vector. It is the algebraic vector as it would play out from the origin. But this is an equivalent vector. Why? Because it's 1, 2, 3, 4, 1, 2, 3, 4, 5 as well. This is called a representation of that vector. Okay? We can have all kinds of representations of that basic position vector. And they're all in this sort of bracket 4, 5, because they're all 4 over and 4 up. So this A1, A2 here, and it's like an X and Y. It's like an X and Y, but it's not pinned down. It's not locked into a specific location. It simply means this vector is A1 over and A2 up, or if we do it in 3 dimensions, A1 on the X, A2 on the Y, and then A3 on the Z. And so this is new kind of notation I think we're going to have to get used to of vector quantities that aren't pinned down. They're not pinned down to a specific place on the coordinate frame. They could be anywhere. Could be out here. 1, 2, 3, 4, 1, 2, 3, 4, 5. And it's going to be an equivalent vector. It's a representation of that basis position vector. Notice the bold indicates that these are vectors here. Okay, determining the position vector. Now let's say that you have 2 points here, point A and point B. Now the vector A, the position vector for those is going to be x2 minus x1, y2 minus y1, z2 minus z1. So that this is the way we find the position vector by if we want to find the position vector for two points. Also, what is the magnitude of this vector? Well, we're just going to use the distance formula, right? It's going to be the square root of a1 squared plus a2 squared plus a3 squared. This again, these are like x, y, z, except they're not locked down to a location. And absolute value, of course, because we're not doing imaginary numbers at this time. Okay, some basic rules about vectors. So to add algebraic vectors, we add their components. So vector A plus vector B is going to be A1 plus B1, the x components, so to speak. Now, by the way, I'm saying x components to give us something to latch onto. As this section goes on to say, vectors don't have to be limited to kind of x, y, z. You could have 10 vector components, a to the n components, where each component is like the price of a particular good in a market or something like that. So we're going to blow the lid on space here and get a little abstract with vectors if you go very far with this sort of stuff in linear algebra and so forth. But for the moment, let's go ahead and get the concept on the table by talking about space, x, y's, and z's. Okay? Now, if you subtract algebraic vectors, we're going to subtract the components. So the vector A minus vector B is going to be kind of A1 minus B1, A2 minus B1. In other words, we're going to subtract the x components, and we're going to subtract the y components. This is fairly reminiscent of stuff we've done before. And if you multiply a vector by a scalar, then you're just multiplying the components by the scalar. CA is CA1 times CA2. Okay, now, the properties of vectors are thankfully very much like the properties of basic math. Commutative property. Vector A plus vector B equals vector B plus vector A. Remember, we talked about putting the initial point on the terminal point of the previous vector. It doesn't matter which order you do it in, it's going to have the same resultant. Associative property. A plus B plus C equals A plus B plus C. Okay? Doesn't matter what order you do it in, it's going to come up with the same resultant. A vector plus 0 is still the same vector, or the identity of addition. And then we have the a vector plus its opposite is 0. Okay. This is the distributive property for vectors. A constant times, or a scalar times two vectors equals the scalar times each of the vectors added together individually. Here's distributive in terms of scalars times a vector. Rather than vector scalar times vectors, we have scalars times a vector. Okay. And again, distributive of multiplication. And then lastly, identity of multiplication. Okay, so basically, we're glad to know that vectors behave like numbers, really, do with these various properties. Okay, unit vectors, and I think this is the last section here. Now, again, don't overthink this. This becomes useful. It's like a different language, really. Just think of it as a game. Don't try to ask why. If you ask why, you'll go crazy. It will be useful, but think of it as another game. So unit vectors or basis vectors basically are a way of coming up with a symbol that stands for a direction. Remember, vectors are magnitude plus direction. So I, j, k are conventionally the unit vector for the x component, the unit vector for the y component, and the unit vector for the k component. What does this mean? Basically, it's a way. See this notation here? This is a way of saying the quantity A1 in the x direction, and the quantity A2 in the y direction, and the quantity A3 in the z direction. So this ijk basically just is a way of saying it's going this way. So this is the quantity going this way, and this is the quantity going that way, and this is the quantity going that way. So this is the quantity going x, this is the quantity going y, and this is the quantity going z, and so forth. And so if you were to write them in this kind of vector notation, the unit vector I is basically 1 in the x direction, and 0 in the y, and 0 in the z. And the unit vector j is nothing in the x direction but 1 in the y direction, 0 in the z direction. And then the unit vector k is 0 in the x direction, 0 in the y direction, and 1 in the z direction. Again, seems awfully complicated, but it really isn't. It's just a way of tagging a magnitude to a direction. So if whatever this number is, it's going this way. Okay? Here's a complicated way of describing a unit vector. Basically, the a's cancel out and you're left with 1. Okay, well, I hope you've survived. This has been the Chapter 13, Section 2 of James Stewart's Calculus textbook, Introducing Vectors.